All right, in section 4.4, we're going to learn about factored form of a quadratic equation. This is going to cover the last general format of a quadratic equation in this unit. So to start out here, factored form of a quadratic equation is y equals a times x minus p times x minus q. Key features here, again, I can see my a value is that leading coefficient in front. And the new thing that factored form tells us is our x-intercepts, or where I'm crossing the x-axis. And a lot of times in a parabola, since I'm in a U shape, I'm going to cross twice, so I'll have more than one x-intercept. So my x-intercepts, if I'm looking in factored form, would be p0 and q0. And notice here that if I'll look at x minus p, I kind of change the sign there, and my x-intercept would be positive p0. So real quick here, what are the x-intercepts if I'm looking at that expression? Again, I could graph this and see where I'm crossing the x-axis, or I could look at this expression and say, okay, I'm crossing at 3, 0 and negative 1, 0. We'll get a little bit more into this after the quiz in our next half of this unit, but for right now, this is really as far as we'll cover with that. So from here, the last thing that we'll talk about in terms of moving from form to form is if I want to go from factored form or standard form back to factored form. And you can even think about this way in vertex form too. So if I want to go from something like factored form or vertex form to standard form, I would want to multiply out all the parentheses, and as we kind of talked about before, that would be the FOIL method. But now what we're going to learn is going the other way. So if I see a function or expression that looks like it's in standard form, I would have to factor it to get it into factored form. So another thing that you might remember from Algebra 1 is when our leading coefficient a is 1 and when it's not equal to 1. The method that we're going to use in this class, I like because it makes it not really kind of matter what my leading coefficient is. We'll start out by seeing when the leading coefficient's 1, and then we'll see a different example when it's greater than 1. It really just adds one extra step. So in our first problem, we want to factor the expression x squared plus 9x plus 20. So what I like to use is the AC method. So basically what I want to do is look at those coefficients, and I want to find two numbers that multiply to give me a times c and add up to give me b. So my coefficients here are 1, 9, and 20. So I want to find two numbers that multiply to give me 1 times 20 and add to give me 9. So some reason why some people don't really like factoring sometimes is it involves guessing and checking. The more times that you do this, the more quickly that you'll be able to think of your factors. So let's say I look at 20, and first I think, 2 times 20 would work out, or 2 times 10 would work out. But then I would see 2 plus 10 would not give me 9, so I need to go back to the drawing board. Another two factors of 20 are 4 and 5. 4 times 5 gives me 20. 4 plus 5 gives me 9, so that's what I want to use. How I'm going to write this out in factored form is x plus 4 times x plus 5, and I'm done. In another example here, now I have negative x squared plus 13x minus 12. So sometimes when I see that my leading coefficient is not 1, the first question I'm going to ask myself is, okay, can I pull out a greatest common factor to make that leading coefficient 1? Here, I'm going to pull out my negative 1 and be left with negative 1 times x squared minus 13x plus 12. Since I was able to do that, now I'm just going to focus on what's inside the parentheses and do the same method. So now I want two numbers that multiply to give me positive 12 and add up to give me negative 13. In this situation, some might be confused of like, okay, how am I going to multiply two numbers and get a positive answer and then add and get a negative one? I would think here, okay, 1 and 12 would give me positive 13. Negative 1 times negative 12 would still give me positive 12, but added together would give me negative 13. So that's what I would want to do here. And when I plug this in, I'm going to leave that negative 1 on the outside as the leading coefficient, and I'm going to be left with negative 1 times x minus 1 times x minus 12, and that would be my final answer. So now let's look at an example when my a value or that leading coefficient is not 1, and we'll see there's really just one extra step in the very end here. My example that I'm going to give is 2x squared plus 11x plus 12. So first I'm going to ask myself, okay, could I just pull out that 2? But I see with that 11, I'm not really able to do that. So I'm just going to have to leave the 2 in there, and I'm going to go from here. Using the AC method, I want two numbers that multiply to give me 2 times 12 and add up to give me 11. So in other words, I want to find two numbers that multiply to give me 24 and add to give me 11. Running through the factors of 24, I'm going to find 8 times 3 would work out here. So I'm going to plug it in like this to start. X plus 8 times x plus 3. Now the last step that I'm going to need to do in the very end here is I'm going to take this 2 and I'm going to divide it by both of my factors. And you're going to see there's 2 different things that could happen here. Either that number is going to divide perfectly into that factor, which I can see here, 8 divided by 2, I'm now going to rewrite as 4. And now when I look, 3 over 2 is not going to divide into an even number. So what I'm going to do is I'm going to move that 2 in front of that x in that parentheses, and I'm going to rewrite this as 2x plus 3. So my final answer is x plus 4 times 2x plus 3. And if you want to make sure that this works, you can FOIL those binomials and see that it matches up to the same thing that I originally had. Now to end this unit, we're going to go through some different kinds of patterns, different kinds of binomials and trinomials that you may see. For right now, write these down. These will be important in the next unit when we go into cubic functions. But for right now, I just kind of want us to just talk about them and write them down for now. So to start, a perfect square trinomial is a trinomial that is the square of a binomial. So for example, something like x plus 5 squared could be rewritten as x squared plus 10x plus 25. So the general pattern here is a squared plus 2ab plus b squared could be rewritten as a plus b squared. A squared minus 2ab plus b squared could be rewritten as a minus b squared. So again, make sure to write those down, highlight them, we'll come back to them. The last thing that we'll talk about today is the difference of 2 squares. So the expression a squared minus b squared is an example of the difference of 2 squares. And how it would expand something like that would be a plus b times a minus b. And you could tell when you're supposed to use this is when it looks like I'm missing a middle b term and when all the numbers that I see in the problem are perfect squares. So let's look at 2 examples. So let's say I want to factor the expression x squared minus 9. My coefficients here are 1 and 9, which are both perfect squares. So the square root of 1 is 1, the square root of 9 is 3, so I could rewrite this as x plus 3 times x minus 3. And now let's look at a harder example to see where this would really come in handy. Now I have 25x squared minus 49. If I tried using the AC method here, I'd be working with really big numbers. So if I could notice, hey, it looks like I'm missing that b or middle term, 25 and 49 are perfect squares, let's use that other method instead. I see that 25 is a squared, 49 is b squared. So my a value is 5, my b value is 7. To factor this, my expression would be 5x plus 7 times 5x minus 7. And again, if I want to double check this, FOIL it and you'll see that it would match up.